The test I am talking about is the P-series test. However, before we can use this test, there must be some conditions we have to follow. It states that for a P-series test to work, it must be positive, it must be decreasing, and it must be continuous. And so what does that mean? Well, just like the series we used, this is acceptable. This is positive, decreasing, continuous everywhere, except for n equals 0, but of course. And now, the usual form for a p-series would look like this. It would look like something n to the p something, n raised to the power of p. Essentially, if you see anything else like that, you can tell that you're going to be dealing with a p-series test. So here's how to solve it. If p is greater than 1, it converges. If p is less than or equal to 1, it diverges. You might be wondering, why is that? Well, this is why we did the integral test first. Let's say we have the series n equals 1 of 1 over n. You know, because of the integral test we did, the series diverges. But there's another way to do it. Since 1 over n is really just 1 to the n, 1 over n to the power of 1, since 1 is equal to p in this situation, p is equal to 1, right? It is equal to 1, and therefore by the p-series test, it diverges. And so it actually helps with a lot, because let's say you had a series of n equals 1 of n to the 2 rooted cube root, right? You would know that if you were just transform this into like a general power, you would know that this would be 1 over n 2/3. Since 2/3 is less than 1, it diverges. Because if we were to integrate this, you would get back a function that would go up. So here's what I mean. You were to add 1, you would see that if you were to put infinity here, you would get infinity, which is why it diverges, which is why the p-series test works so well if you're just looking specifically at function or at series that have the formation of infinity n equals something 1 over n to the p, which is why it works so well. Now we're going to be moving on to another test. We're going to be moving on to something which is actually one of my favorites, which is the alternating series test, or AST in short. The alternating series test states that if you had a series and it was alternating, xn of something, if it was alternating, you could find if it is continuous by taking the limit of the absolute term as n approaches infinity, and it will be equal to 0, and that the same term of n plus 1 is less than or greater to the normal sequence. And here's what I mean. Say we had the series of -1 n plus 1 over n. So by using the rules that we have just stated, we take the limit as n approaches infinity. We take the absolute value of this. So we do 1 over n. We can see that's equal to 0. From here, what we have to do is just add 1 over n plus 1 and see that as the denominator increases, therefore, this sequence it is less than 1 over n. Therefore, series converges. Now, the problem with this, well, not problem, but the condition that must be met is that this has to go. This has to be bypassed. This has to pass. If, I'm sorry, this one. If your first condition that the limit as n approaches infinity is not equal to 0, then your whole thing just diverges. Because that will be going back to the nth term test, where if we take the limit as n approaches infinity of a specific sequence, and it's not equal to 0, then it diverges. And so it has to pass that rule. But if it passes, then usually every other test passes the second condition as well. And so another example would be the alternation of -1 n plus 1 over n squared. From here, you take the absolute value, so it'll be 1 over n squared, which is equal to 0. And then you can see that it's less than 1 over n plus 1 squared. It is less than 1 over n squared. And so therefore, series diverges. And now there's another thing that with this series test you can test. It is called conditionally convergent. And here's what I mean. So let's go back to the series of -1 n plus 1 over n. It states that a series to be conditionally convergent, the original series has to converge. However, if we take the absolute value of this series, then for the original series to be conditionally convergent, the absolute value of that series has to diverge. And here's what I mean. So, the series of infinity n equals 1 of -1 to the n plus 1 over n, if we take the absolute value of that, it would just be the series of 1 over n, right? We know that 1 over n diverges because of the last two tests we did, the integral and the p-series test. Therefore, the original series is only conditionally convergent. And what does that mean? I have no idea. I honestly have no idea what that means if it conditionally converges. I even asked Mr. Cousins and he was like, I don't know. So I do not know why that is. But essentially these are your first few, series sequences tests that you're gonna have to do. There's about 6 more, but I'm not gonna cover those because there's so much to cover. And so I'm gonna leave you off with a practice problem. So let's say you had the series of n equals 2, then you have 1 over n, natural log of n to the squared. Would this series converge or diverge? Please leave your answer down in the comments, and I'll respond to you if you got it right or wrong. That is my practice question. I am out. I'm gonna probably gonna make another video after this because I have no life. Thank you for watching. Like, subscribe, share, do what you need to do. Thank you for watching, and goodbye.